Using the advancements of artificial intelligence research, humanity is now capable of tasks that previously seemed impossible. Imagine pathologists spending hours manually segmenting tumors or calculating the density or volume of specific proteins to classify patients as being ill. With the help of AI, we can now segment thousands of CT scans and immediately get told what is wrong with patients. Each image is an input tensor consisting of a batch size, height, width, and channel dimension. Each value in the tensor tells us the intensity of each pixel. This way, we can get a colored image. The network consists of a sequential, fully convolutional network with a contracting path, an encoder, and an expanding path, the decoder proposed by Ronneberger et al. This network was introduced in 2015 and has revolutionized image segmentation. The network efficiently captures high-res and low-resolution features to capture complex patterns in images where every pixel matters. The images get through a convolutional layer, which applies a kernel with a 2x2 grid and computes the weighted sums over the image. This helps detect features by the model, and new channel dimensions are added, where each channel shows the different features the model has learned from the input data. Next is the rectified activation unit, which gives the model more positional information by transforming the negative values to 0, where 0 equals black pixels. Next is the max pooling layer, which condenses the images. It increases the proportions of non-black pixels to black pixels, effectively capturing high-resolution features. The result is a feature map with fewer features. This fully convolutional block happens 4 times, reducing the feature map and capturing high-resolution features before moving on to the expanding path, the decoder. In the decoder, we apply what we call a transposed convolutional layer. A transposed convolutional layer is an upsampling layer that generates the output feature map greater than the input feature map while concatenating the corresponding feature maps with the exact dimensions from the contracting part of the network. This happens 4 times, effectively retrieving the low-resolution features from the training data. Ultimately, we apply a softmax function to map the model outputs to predicted probabilities for each class by each label, ensuring that the model will segment the pixels of interest. Throughout the training process, we utilize multivariable calculus to backpropagate the network and optimize the cost function, which is the cross-entropy or dice loss in terms of the weights. The weights connect the neurons and establish a difference between the ground truth segmentations and the predicted segmentation. Each weight gives information to the model about a distinct pattern for the model to recognize and use for future predictions. A formula to change the features would be a system of equations consisting of tens of thousands of partial derivatives of the cost with respect to each feature and solving for each feature. This is impossible, so we use the gradient descent algorithm. We use the gradient descent algorithm to compute the partial derivative of the cost function with respect to the weights and figure out in which direction we need to move along the tangent plane to minimize the loss function. The learning rate alpha determines how much we need to tweak the weights to descend downwards onto a critical global minimum point. Researchers have found advanced algorithms to overcome challenges arising from the limitations of gradient descent, including stochastic gradient descent and the atom optimizer. The algorithm uses the chain rule to compute the partial derivative as the cost function, depends on the kernel initialization results, the rectified linear function, and the max pooling layer. For each epoch, the algorithm computes these partial derivatives for all tens of thousands of neurons for each layer. How do you feel about living in an advanced civilization where we can find out every illness you suffer from with simple scanning and a press of a button from a computer? This is the future as AI will progress and advance in our society. AI is already implemented in every industry and has shown high efficacy in optimizing processes and work tasks. We may soon be able to delegate full power over to the machine. A neural network resembles the ones of a human brain. All the connections found within the neurons in your brain form the backbone of learning and memorizing. Who do you trust the most? A machine that can learn about a specific topic indefinitely, or a waste man doctor who only has money on their mind?